Here we go. And the floor is yours. Please go ahead,
Okay,
Tim.
hopefully you can see my slides. If not, sort of gesticulate wildly and I'll put them up.
Okay.
Thanks a lot for inviting me. It's good to be here. I should warn you that I'm a computer scientist and professor at ETH, but I don't really work in high performance computing. So this could be probably classified as low performance computing, which I think is what the rest of us do. But I'm going to talk about operating systems, and I think it matters for pretty much all fields of computing. And in particular, I'm going to try to persuade you that the operating system is not what we tend to intuitively think about as the operating system of a computer. So what we call the operating system in practice is not actually behaving in the way that you would expect an operating system to behave. Something else is doing what the operating system is doing, and it's quite scary what it is that's doing what the operating system is doing. And the reason for this is that what real hardware looks like and what modern operating systems expect the hardware to look like have increasingly diverged. And I'll talk a little bit about that. I'll talk also about how we as my group came to the realization that there was a serious disconnect in a sense between operating system design and hardware design, and as a consequence between actual software design in general and hardware design. And so the response, which I'll talk actually in a sense less about, this is more a talk about the problem than a solution, is to try to build an operating system that actually really does reflect the hardware. And hopefully at least I'll give an idea of the challenges of that in this talk. First description is, first step in any case is to actually sort of write down what the hardware really does. So how did I get to this weird point? So a long time ago, my group and I, along with some friends at Microsoft Research and some other places, wrote an operating system. It was a long time ago. It was 2007. And 2007, some of you may remember, there was some sort of excitement in the computer architecture community. We're reaching the end of Dennard scaling on transistors. And so what's happening was that it became increasingly difficult to speed up an individual processor, individual core. We're reaching the limits of instruction level parallelism, pipelining, and so on and so on and so on. And so this was the sort of the dawn of the multi-core era. The confident expectation was that there will be many, many, many cores on a chip. Okay, there was devices like the Intel Xeon Phi accelerator, for example, which had really quite a large number of sort of x86 cores on a chip. A variety of other things appeared. Core counts were confidently expected to go up to very high numbers. And there was concern that operating systems, as well as other software, wouldn't necessarily scale very easily to this large number of cores and this degree of parallelism. And so there was concern that this might involve rewriting quite a lot of the world's sort of system software. Okay. So we looked at that as an operating systems group. I just started at ETH. I had the advantage of tenure. And so you thought, well, there's going to be thousands of cores. This has some interesting implications. Cache coherence, for example, might not be global in a computer system. Shared memory might not actually scale to that kind of size. Cores, however, are going to be very plentiful and very cheap. It's possible that not all of them can be turned on at the same time, but there will be a lot of them. We also thought that there'd be some other motivation as well, and that was something that we saw happening already, which was that hardware was going to become increasingly heterogeneous and diverse. Okay, new SoCs kept appearing every few weeks for mobile phones and for embedded devices, but also increasingly for servers. And it was interesting that adapting an operating system to a new hardware platform was going to be a problem. And indeed, this is a problem. A huge amount of software engineering effort goes on inside, for example, mobile phone companies like Samsung, in response to every new SoC that comes out that they need to get Android working on, for example. And so you're looking at a very diverse, very rapidly changing hardware market. Okay, and it is hard to evolve operating system software. In fact, one of the insights was that hardware was now changing much faster and evolving much faster than software could at the time. And of course, applications themselves are going to have to run over a very heterogeneous set of cores, GPUs, but other kinds of accelerators were appearing. And, you can see where this is sort of going. So we, at a university, but with some friends in Microsoft as well, we decided that we would adopt as a project, we'd try a very different approach to writing an operating system for a single machine. And so he wrote an operating system. It's called Barrelfish. It was based around the idea that the operating system should view the machine as a distributed system, even though it was all in a single box. So we didn't share any data at all between cores inside the OS. Applications could run in shared memory, that was just fine, but all communication, coordination between the operating system bits running on individual cores was done by message passing. Okay. Every core could potentially have its own implementation of the operating system, and this meant that you could deal very easily and very nicely with, for example, heterogeneous cores. The operating system state, if you think about this as a distributed system, obviously the state is either partitioned or partially replicated, but you always access the state as if you're accessing a replica in a distributed system. And this means that, operations tend to be kind of split phase. If you're updating state, maybe you've got to go through an agreement protocol, for instance, to do this consistently. Depends on, the particular use case. But effectively, invariants in Barrelfish were enforced by distributed algorithms, whereas in a conventional shared memory kernel, invariants are enforced by locking and or wait-free data structures in shared memory. Okay. So we just decided to take this kind of extreme point in the design space and see what we could do, is build an operating system around this. And we ended up with, the kind of model that you sort of see here. You've got a bunch of sort of hardware and potentially heterogeneous kind of hardware accelerators here, sometimes running software, system software. Above that, you've got, replicas of operating system nodes. These are all independent. They communicate with asynchronous messaging, and those form the functionality of the operating system. Above that, you run applications, conventional applications. They can use shared memory if they like. That's fine if cache coherent shared memory is available. But the operating system itself doesn't require it. It didn't require shared memory, and indeed it didn't require cache coherence to function. So, the surprising thing about this, it was a big project, and many years at it. What was interesting about it, what was very pleasing about it, was that you could build an operating system this way, and you could deliver performance that was essentially equivalent to Linux on this, on a regular PC NUMA server or something like that. So, we could run the Barrelfish web server ran on this, for example. We could run databases, SQLite, PostgreSQL, other kinds of things. It had an open SSH server, it had a TTY subsystem and that kind of thing. All of this was, essentially written for this operating system. It had a very different interface, I have to say. But it would support a virtual machine monitor. You could boot a Linux kernel in a VMM. Managed to get rump run running, so you get BSD components running, for instance, like that. And rather entertainingly, inside Microsoft, they used it. They could actually run Microsoft Office on it. So I've actually seen Andrew Bauman, my colleague, give a presentation on Barrelfish on a laptop, running Barrelfish on the metal using PowerPoint, which is quite an achievement for a research operating system. This was using the drawbridge system that you may have heard of at Microsoft that enabled you to bundle Windows applications up into static binaries. And it supported a wide variety of interesting bits of hardware. Weird SoCs that we ported it to. We deliberately went for heterogeneous machines, even though our main goal was to go for sort of scalability. And that was interesting because what came out of it at the end was that we expected the main motivation of Barrelfish to be scaling an operating system to thousands of cores. That didn't happen, right? You don't get machines with 1,000 general purpose cores in them these days. They're going up slightly, but at tops you're getting about 256 threads in a box, right, on the CPU. And cache coherence has been still pretty global across a single machine. So that motivation didn't really happen. Okay, and that's the reason that, it's probably connected by the fact that Linux runs just fine on modern server machines. Okay, Linux scales perfectly enough to deal with the number of cores that you get on a modern server machine. What did turn out to be much more important in retrospect, the benefit of hindsight, was that hardware was indeed very highly heterogeneous and very diverse, and this just got much worse. And so we are seeing increasingly diverse systems, increasingly complex systems. And the thing that happened with Barrelfish for us, the thing that gradually dawned on us, was that computers, and in particularly computers for sort of mobile devices, were not what we expected a computer to look like as operating systems researchers. And that was kind of a shock. We'd been around this block several times. Okay. So I want to sort of talk about, what a real computer looks like. And if you look at a textbook on operating systems, they describe the model that an operating system has of the hardware. And it looks a little bit like this. Okay. And this is from, Brown and O'Halloran. It's from 2011. We use this textbook for teaching systems programming at ETH to second year students. But it actually, it has a diagram here. It says, here's a computer, and you've got, all the usual sort of stuff. You've got a CPU, to have more than one CPU, of course, these days. An I/O bridge, which then talks to main memory, and then an I/O bus that talks to various peripherals. And that's essentially your computer. And what the object of the exercise, of course, is to run enough software on the CPU or the cluster of CPUs here that manage all the rest of the machine. And this is basically a PDP-11, right? And this is the kind of PDP-11 that, Dennis Ritchie and Ken Thompson used to write Unix, in effectively the year I was born. Okay. The problem is that this is not really what a computer looks like, as you probably know. This is a typical sort of mid-range system on a chip that's used in the automotive industry quite extensively. It's an NXP IMX8. It's quite popular, it's quite successful, and crucially from our perspective, it's quite well documented. But as you can see, it's quite complicated. This is actually taken from the manual. And crucially, all these circles here are the cores that we know about from the publicly available documentation, which are running some kind of system software. Okay, and there are a lot of them. Each of these is a cluster of cores, right? We've got two sort of clusters at the top. There's an M4 CPU, Cortex-A35 CPUs here, but there's a variety of other things down here. Secure coprocessor, a different system control unit complex down here, and so on, and so on, and so on. All of these are effectively, small groups of cores, all running different kinds of operating system software. If you want wondering why Linux runs, it actually runs on these Cortex-A35s up here and nothing else. And indeed, Linux is not really aware of what resources it can manage on any of the rest of the system. To the rest of the system, these things are dumb devices. And so that's kind of interesting. And that's just one SoC. If you look at a different SoC, this is Parker, or look at a different SoC, this is Kepler or something like that, or a different SoC. This is a Texas Instruments OMAP from a while ago now. You see the same thing. There is a very large number of different kinds of processors on here, all of which are running different kinds of software, and all of which are connected in different ways. Indeed, if you look at the manual and you read the security bits of the manual, it's pretty clear that a lot of this hardware is designed to sandbox Linux as a piece of software that the hardware doesn't really trust. Okay, on the OMAP, for example, all of the, I don't know if you can see this on the slides, but all of these little yellow boxes here on the interconnect, you can see a few of these things here. These little yellow boxes are firewalls. They're programmable firewalls on the interconnect that allow you to sequester off bits of hardware or protect them in various ways. Think of them as very simple system memory management units. So the idea here is that Linux is really constrained to only see a very small amount of the machine, and yet a lot of the rest of it is kind of there, and it's documented. It's running real software, and so there's a bit of a mismatch here. Okay. Another thing that's interesting about a machine like this is that it violates many of the basic assumptions that you would expect to see in the classical model of a machine that operating systems assume. So, for example, operating systems provide virtual memory. They map virtual addresses in a virtual address space to physical addresses. The idea is that everything in the system sits at a physical address, memory mapped IO or DRAM, and that you can access something just by specifying its physical address. That's not actually true anymore. And so there's an awful lot of different kinds of cores, a lot of different kinds of devices on a chip like this. And what's interesting about them is that there's no real universal view of what an address is. This thing has been basically put together by a talented engineer working late at night on a CAD system. And so if you take one device, okay, like this GPT-5 general purpose timer here, okay, it can be accessed using a wide range of physical addresses depending on what core you're actually on. If you are on the Cortex A9, which runs the application processors, that actually boots Linux, for instance, it actually appears at 2 different addresses. It's aliased in the address space. Okay. However, if you're running on the DSP, which runs its own sort of system software, well, it shares a physical address for this timer with the application core cluster, but it also has its own private address, which is different, and different from the CPU's different address. And indeed, there's a Cortex M3 over here that you can actually use and is recommended for use by applications. But that just sees the timer at a totally different address as well. Okay. So this is violating many of the assumptions that an operating system would tend to make in the classical design. The only reason this works, of course, is that the operating system in question here, Linux, is completely oblivious to all of this. All it cares about is what runs on this A9 here, and all the rest of this stuff is largely invisible to the operating system. It's not designed to handle it, and it has no desire to do so. So is this a problem? Right? I mean, these things work, right? I can still, make phone calls. I can still use, apps and things. Well, these are examples of assumptions that operating systems make and which they base their correctness. And if these assumptions are violated, like there's something else happening in the system that they don't take care of, this can result in incorrectness, it can result in bugs, it can result in unreliability, and it can result in security problems. So here's an example from Black Hat a few years ago. If you've got a Qualcomm mobile phone, if you had one in 2019, somebody could literally walk past you with your phone, and you didn't need to be connected to any Wi-Fi network or anything like that, but they could essentially take over your machine remotely over the air. Okay, and the way they did this, it's an interesting description of it. They sent a malformed Wi-Fi beacon packet, so you didn't need to be bound to a network. This compromised the process that was running on the processor on the phone that dealt with the Wi-Fi stack, not the processor on the phone that was actually running Android or whatever phone operating system you happen to like in 2019. From there, you could exploit a vulnerability in that operating system to compromise the kernel, and thereby break into another process running on that processor that happened to deal with the modem. That process was trusted by the Linux kernel running on the application processor in terms of what it described it needed to do in terms of accessing main memory. That would cause Linux to reprogram the system memory management unit and allow the original process to DMA data over the Linux kernel running on your application processor. And at that point, you've got root on the machine. Okay, and this can all happen in a fraction of a second or so, just simply by walking past. Now, the problem here is that Linux can't really solve this problem because the problem isn't on Linux. The problem is on another core that has access to memory that Linux needs and is reliant on. And that's inherent in the design of the hardware. If you could imagine possibly, I don't know if this is possible, it's possible to write an operating system that ensures that this doesn't happen. The problem was that the operating system here was not written with that possibility in mind. And in fact, there are 2 different operating systems that are interacting rather poorly here. There's the one on the Qualcomm chipset and there's the one on the application processor. There are many such attacks like this. Okay, this isn't just a Qualcomm thing. I'm not beating up on Qualcomm. Broadcom have another one of these. A lot of them keep appearing every now and again. Sometimes they're called cross-SoC attacks because it's one part of the chip attacking another part of the chip. And with, you can imagine with chiplet architectures and things, this is only going to get a lot worse, as long as the view of the operating system is kind of really restricted to, one corner of the chip that happens to be running Linux. These things can even happen in the smallest devices. So the folks over at Oxide Computer, who make very nice kind of rack scale cloud computing facilities, they have a very small root of trust in their rack that's based on a ST Micro, fine Swiss designed microcontroller, bunch of Cortex M33s on it. And that thing, they've written their own operating system for. It's called Hubris. It's quite cool. It's a small embedded operating system to run a root of trust on. And there's a ROM, which they use to store the code. And there's a woman at Oxide who kept finding vulnerabilities in an onboard processor on the ROM. And so it's not simply that there's big things like DSP processors, baseband stack processors on SoCs that can cause bad things to happen to, the operating system running in the corner. There are vulnerabilities in ROMs. that happen to have embedded processors that can cause problems as well. And they found at least 2 of these things at hydrogen peroxide because they're kind of paranoid about this kind of thing. So these are not just bugs. This is a systemic issue in operating system design. The hardware is very complex. The documentation is often imprecise. Operating system code is almost always ad hoc. But the big problem is that fundamental operating system assumptions are wrong. Operating system assumptions that say the operating system is in charge of all the devices on the system. The operating system can protect all of memory and has the right model for protecting memory. The operating system, assumption that says that there isn't another operating system invisibly running on the same machine that I might be in conflict with. And until those assumptions are questioned, these bugs are just going to keep appearing, and we're going to continue to have vulnerabilities in phones and embedded devices all over the place. And that really, those assumptions are kind of baked into the very architecture of a monolithic kernel or a microkernel, which assume they're running on a small homogeneous cluster of cores. Okay. There was even a paper on a brand new microkernel from Huawei. I was lucky enough to shepherd it at OSDI a couple of years ago. It's called Hongmeng. It's now in all the Huawei mobile phones. It has exactly the same issues. It was a fantastic piece of engineering. It's great stuff, but it suffers from exactly the same problem. So what did we try and do in response to this? Right, we had a go at saying, well, can we get a handle on this somehow? Hardware is too complex, but it's the complexity of hardware and the fact that operating systems are ignoring the complexity of hardware because it's too difficult to engineer that is causing the problem, perhaps. So can we get a handle on the complexity of the hardware by writing it down formally? Right? Let's throw some computing at the problem of dealing with the complexity of a modern computer. So we'd start by going through the manuals and try to write them down in some sort of formal language that captured what we need to know in order to reason about security and correctness in an operating system on the machine. Okay, so the initial early attempt to do this, the kind of conceptual model we used was something called an extended decoding net. Okay, and this was a sort of, effectively it's a graph. It's a directed graph, and the root nodes of the graph are things that we call sort of physical contexts. They're things that can execute bus cycles, like their cores, effectively. Except that we also model any device that can do DMA as, it's just another core whose software we can't see. So devices and cores are not distinguished in terms of what they can do to the system. And these are the root nodes of a directed graph. The leaf nodes of a directed graph are things that can actually be accessed in the system, DRAM or device registers, memory mapped IO registers. And then the structure of the graph, the internal structure of the graph, talks about how addresses are remapped through the system. Okay? The internal translation arcs essentially are translations between address spaces, and nodes are logically different address spaces in the graph. Okay? And those translation arcs might be programmable, might be memory management units, TLBs, lookup tables, protection units, where effectively the address is translated into a pass-through or reject. For instance, protection units fit into this model quite nicely. And then, the address spaces are sort of, fully decomposed. So for example, if you've done any PC hardware hacking, you might think that all of the cores, it's convenient to think of all of the x86 cores on a machine as seeing the same, same view of physical memory. But actually, if you look very carefully, that's not true. They all have a local APIC. It's at the same address on every core, but it's a different local APIC. And so we would represent that as saying, well, every core has actually got its own physical address space. And then regions of that are translated to the local APIC. And then the rest of that address space is translated to a big shared address space, which then gets translated to other things in the system, PCI subsystems and whatever. So you can build a graph that represents a computer and how addressing works in the computer. And when you do that, some interesting things happen. So here is an example of the kind of graph you get. This is actually not a real process. This isn't a real board. This is the simulator that ARM make available for their Morello test platform. We actually have a real Morello platform here, but the simulator is complex enough that it's worth showing here. The actual Morello board that does, cherry capabilities for ARM and things like that is actually more complex than this. But this is the FVP, the fixed virtual platform, the simulator that ARM give. And so what's happening here is that you read this graph roughly left to right, And so stuff on the left, are root nodes. These are things that can execute bus cycles. Stuff on the right are leaf nodes. These are things like devices and memory, where cycles end up and get turned into reads and writes on memory. And so as you can see, this is quite a complicated thing. Okay, it's more complicated than the rather simple picture of a computer that you see in a textbook. If you know Morello, you'll know that there are 4 modified Neoverse cores that are actually implementing cherry capabilities. And you may wonder where they are on this diagram, since there's only 2 big things on there that can access lots and lots of bits of memory. Well, it turns out there are these little 4 boxes here. That is the thing that is running the so-called operating system on a machine like this. Okay. So why do we focus on memory access? It turns out that most vulnerabilities in operating systems tend to come down to memory access. Confidentiality violations, obviously, in memory access, but also integrity violations tend to involve writing something to memory that you weren't supposed to write to, things like that. There are some things that don't fit into this model. Power management, I²C, things like that don't. Oddly enough, interrupts do, because interrupts can be modeled very nicely as an extension of this graph. Oddly enough as well, this graph here is obviously acyclic, but not all of them are. If you had, for example, back in the early, mid-2000s, if you had a machine with a Xeon Phi accelerator, the decoding net graph that explained that machine was cyclic, which, is an interesting thought when you think about what that means with in terms of address translations. Okay. This is, by the way, the decoding net for the IMX8 automotive SoC that I showed you earlier on. It's a nice chip. We use it for teaching here, for example. People write full operating systems for it as part of the operating systems course at ETH. The 4 application cores are said down here. All the rest is other stuff. And so there's some interesting features here, okay? So this is as far as we can tell from the documentation. We've spent a lot of time working with the documentation. This whole mass in the middle here, all of these arcs, are a pretty complicated, comprehensive protection unit that is designed to be able to give you very fine-grained access control between all of the rest of these things here, all of which can access memory, and all of the stuff over here, which are all the kind of resources that can be accessed. So it's pretty dense, and they've tried to give a fair degree of fine-grained access control here. It's not quite as good as this graph shows, though, because basically this is a tagging unit and there are only 16 tags you can use. So every ingress here is marked with you can program each one of the ingresses here, or each one of these boxes can be programmed with one of 16 tag values. And every egress is marked with one of 16 tag values. And if they don't match, then the access is denied. So it's kind of inflexible. But the complete superset of all the possible access control things is summed up by all the arcs in that graph there. Okay. The other interesting thing is, which will come back later in this talk, documentation kind of sucks. So these are devices here that we know can do something on the system. They are cores, they're programmable, but we don't know what they can do because the documentation is kind of silent on that, which is also perhaps a cause for concern. That came out of translating the documentation into a formal specification. So what you can do is you can take a graph like this, project it, flatten it, and you get what's called a hardware access control matrix. Right? You take that graph, you project it, what are all the root nodes, what are all the leaf nodes, what can access what, and this gives you the complete set of possible accesses in the system, irrespective of, before you try and configure any protection units in the system at all. And you end up with diagrams like this. Here it is for the IMX8. You can see that an X here means that access is allowed, and a blank space means that access is not allowed. This is by default. So obviously any operating system, any firmware or anything is going to be configuring the protection units to remove these X's and replace them with spaces to lock the system down further. And of course, that is in practice what happens when you boot. You've just got to figure out what you want. And it'd be nice if there was some sort of formal tooling to do that. Right now, there isn't. So that's SoCs. Now, of course, a lot of us work with servers and everything like that. Servers feel like they're simpler. I mean, there's so many devices on here. There's so much stuff running on a phone. Whereas, a server sitting in a rack with, maybe some smart Ethernet cards, maybe a GPU, surely is not going to be quite as horrific as these kinds of, automotive or phone-based sort of parts that we've seen. So the other reason we ended up here, and this is a different perspective on the same problem, is that a few years ago we built our own computer for research. Okay, so it's called Enzian. Looks a bit like this. It's like a 2-node NUMA system. So it's a 2U rack mount case, EATX board, full-size EATX board. It's got up to about 1 terabyte of memory on it. Think of it as a 2-node NUMA system, except that one node is a 48-core ARM v8A server class processor, 2 gigahertz, so reasonable processor, 128 gigabytes of DDR4. The other NUMA node is a big FPGA. It was the biggest, fastest FPGA that Xilinx made at the time. And that also has a lot of memory on it. And crucially, in Enzian, from our perspective, this is kind of still a fairly balanced system, right? There's a lot of network bandwidth on one side, a lot of network bandwidth on the other side. A lot of storage on both sides, bit of PCI Express on both sides. But crucially, which is not the topic of this talk, but it's something that we're very pleased about, the processor and the FPGA exchange cache coherence messages, and it is the processor's proprietary cache coherence protocol, which is re-implemented. We re-implemented that on the FPGA. Why would you want to do that? I can talk about that offline. There are many reasons you want to do that. It was built, though, as a research computer. It was optimized for extreme flexibility, deliberately over-engineered, deliberately instrumented in all kinds of ways. We have 14 of them here. We use them quite a lot. We have some external users who use them. They've allowed us to explore the hardware design space in a way that we couldn't do if we were relying on the experimental equipment that vendors typically, will lend to us or give us as a research group at ETH. But crucially, we had to build this, right? We had some help from a board house in Germany, but we had to design it. We had to design the schematic, and we had to really get to grips with what a real server actually looks like. And again, as with Barrelfish, we learned an awful lot as operating systems people about what a computer looked like and how an operating system didn't quite correspond to this very well. So, crucially, there's a thing on Enzian, but there is on every server that you buy, called a baseboard management controller. We thought we had ludicrously over-engineered our baseboard management controller. We used a Xilinx Zinc processor, two-core Cortex-A9, Zinc 7000, running the default installation of Linaro Linux and OpenBMC. It turns out that we were not massively over-engineering it, that most other servers have a very similar kind of level of power in their baseboard management controller. So this leads to all kinds of interesting questions. So what does a real computer look like? Here's the Unix model again. And what I've done here is I've added the fact that we have, user mode and kernel mode. This is typically what an operating system textbook will talk about. There's a mode switch between user mode to kernel mode, allows you to virtualize the machine. Okay. But as you guys probably know, modern servers are slightly more complicated than that. Here is a reference design from Open Compute. You can see that there are many CPUs. Those CPUs are multi-core. There are many networks. There's PCI Gen 5 here. There's NVLink. There's Ethernet. There's NVMe. There's local memory. There's remote memory. There's a whole back-end network between the GPUs here, and so on, and so on, and so on. This is a complicated topology. More than that is that each one of these things has something called a baseboard management controller. It controls power and clock sequencing to everything on the board. It basically does all the power management on the board. It involves running hundreds of thousands of lines of code before you can even take the CPU out of reset. Okay. Typically, these things are running an old version of Linux. In the case of Enzian, this thing came with Linaro 4.0 kernel. They're network facing. They have an Ethernet. They're running an unpatched web server that you can use for management that sits on that Ethernet port. The software inside that is called OpenBMC. It's an open source project. You can find it on GitHub. It is based around dbus, bash, and Python. This is used to control the power and clock management inside your server. You might be worried about that. We used that because it was open and available and we didn't know any better. And we thought that obviously real companies would use something more professional. And then we talked to the Google server commissioning people, and they said, yeah, that would be great, but all the vendors use OpenBMC because it's what they understand. They don't run it on Zinc, obviously. They run it on almost always an A-speed AST 2600 or 2700, but it's essentially the same problem. I was quite shocked about that, but now the Google said, yeah, we would love to do, not to have that, because it's a security headache for them as well. They have some very interesting ways around it that I probably shouldn't talk about. But this is a very complicated thing in and of itself. It's another SoC. It's almost as complicated as the SoCs I just showed you. And this is the thing that is controlling everything else in the server before you even get to run your own application code on this machine, or even run your own operating system on this machine. Okay. CPUs, as you probably know, also have all their own management engines, sometimes on the CPU. Big, x86 CPUs tend to. The Intel management engine, famously discovered to be running Minix a while ago. AMD have their security processor hardware. It's running a bunch of ARM cores with its own operating system and stuff like that. So there's all these other hidden cores in a server as well. Not only that, the server itself, the CPU itself, has many different modes that it can operate in. And the CPU, the way the CPU accesses memory, is enormously complex. If you go off and look at what all the different registers do in terms of changing how the CPU accesses memory in different processor modes. And this leads to a whole new class of security problems. So, for example, you may have heard of this thing from last year at DEF CON. This is a really cool, it's a really cool presentation, actually. These guys were very ingenious. But ultimately, they found a way where if you're running in the kernel, right, which is basically ring 0. Sorry, I get them around the other way with ring 0 on an x86 machine, so you're in the Linux kernel, you can execute arbitrary code on an AMD processor in system management mode, which is ring -2, which is enormously privileged and has the ability to actually cause permanent damage to the hardware. And they did this by using some facilities to remap accesses to memory, violating the assumption that a physical address space was uniform, and tricking the machine into taking a trap at the wrong time and then jumping to the wrong address and actually jumping to a trampoline that was in a handy PCI Express device, which they could map into something that the processor didn't realize was not its secure system management mode code memory. It's a very interesting kind of thing. It was it's a sequence of operations that can do this. You just write this register, write this register, write this register, and now the processor will do an instruction fetch from some memory in system management mode that it should never be able to access in system management mode. These things are complex. All these interactions led to this kind of bug. This bug affected 20 years of AMD processors, and some of them could be fixed with microcode patches, some of them could not. If you look at ARM, which is supposed to be simpler, this diagram is from the ARM website. Okay, this is from the ARM official documentation. This is an ARM V8 or V9 CPU doing its thing, okay? And what you've got is different exception levels, 4 different exception levels, 3 to 0. 0 is sort of effectively user space. But beyond these kind of, these 4 things here, you've got all kinds of different things running. In confidential compute, you've got a realm management monitor. Then you've got a whole bunch of different secure worlds, each of those realms is running its own operating system kernel. Each of those is running different applications. That's just the confidential compute world. The regular world has a hypervisor above that. It's running multiple operating system kernels. It can also be running device virtual machines that deal directly with devices like GPUs. It can also be running, of course, an operating system kernel directly on the hypervisor, non-virtualized, and so on. Plus, you've got good old Trust Zone over here, which is a secure partition manager. That's still there, and that's still running code. That is partitioning its part of the world into a variety of different things. And, if we take our original view of what, Linux was doing, what Unix was intended to do, there are many, many instances of that in this picture. And so one might look at this and say, well, hang on, what exactly is the operating system here in a useful kind of way? And so what I want to do is to introduce a term that I think is very useful here called the de facto operating system. Here are 2 definitions of an operating system, right? One is that it's simply the set of kernel daemons and user mode libraries. You'll find this in some textbooks, particularly older textbooks. It's very applicable to something like Unix. I don't like this definition because I much prefer the one you find in other textbooks, more modern textbooks, including, well, here's the one that we use for teaching here. It's Operating System Principles and Practice, which is the operating system is the body of software that multiplexes the machine's resources, abstracts it, protects different principles from each other. If I apply that second definition, I can walk up to a computer and I can look at what software is actually doing this. And I can say, that must be the operating system by definition. And so you end up with something called the de facto operating system of a machine. In something like the IMX8, the de facto operating system is everything that's running as system software in all of these cores. Right? And every computer that is currently dialed into this Zoom conversation is running a de facto operating system. And that is not, I'm sorry to say, iOS or macOS or Linux or Windows. Each of those may be some small component of the de facto operating system, but the de facto operating system is something completely different. What is it? The problem is it doesn't have a design. Nobody's designed it. Because it doesn't have a design, it doesn't have any correct behavior. There's no definition of what it means for this to work because nobody knows what it looks like. If you can't define what its correct behavior, you can't deliver any trust guarantees from it. Right? There's no way to trust something if it simply has no definition of what its correct behavior is. If you can't say what correct behavior of this system is, you don't have any way to improve it in any kind of rigorous kind of way. Right? You don't have any way to reason about the system if it has no definition of what correct behavior is. It doesn't have any definition of correct behavior because it doesn't actually have any design. This is an extraordinary state of affairs to an operating systems person like me. It's kind of, oh my God, my entire field has suddenly sits on very shaky foundations. We got into this mess of various reasons. I won't get into any sort of blame game. I think it's this emergent behavior from the community. There's a number of different sort of, factors, but no one organization, role, or anything like that is really to blame. But we're in this mess, okay? And the problem's not going away. New operating systems are appearing all the time. This is the Hongmeng kernel from Huawei. It's a great paper, but it shows exactly the same problems as Linux does in that sense. And so we haven't made any progress in solving this problem. So what do we do? So I don't know, but we have some ideas. And so in the last bit of the talk, I'll talk about what our ideas might be and whether they might work. They're following on from the kind of thing I talked about, but we're trying to get more of a handle on what the hardware is doing. So getting a bit more level of detail than we had with just that decoding net. Remember that decoding net was kind of vague. It said, here's all the possible things you could do. It didn't really capture how you can program a system to try to reduce, the number of open cells in that hardware access control matrix that I showed you earlier. So what we're trying to do is to come up with a more detailed definition. Take this decoding net thing and instead write something that looks a bit more like it, but is more of an executable specification. Okay, and there's an example of that over on the side here. And this is based on how SoCs are actually designed. So in practice, the way these things come about is, somebody comes up with a hardware design. That hardware design is then synthesized into some real SoC hardware. Okay. Then it is translated at the same time. The hardware design is translated into a hardware manual, sometimes partly online, more generally by a poorly paid summer intern. That hardware manual, together with a whole load of published errata that may come out afterwards, is manually translated by an operating system engineer into system software, some port configuration, bunch of extra additional processes for, say, Linux in the case of an Android phone. That system software then executes on the real system, and it also configures the system in a particular kind of way. This is simply what happens today with modern computers. Okay, and so what we're going to do is sort of augment that in various ways. So we're going to extract somehow a formal specification of what the hardware is doing. We're going to extract this from the manual. We're going to look at what the system software might do, and we're also going to look at, we can extract a running configuration from a system. We don't need to do all of these things, but initially, we can get our sources from various different places. That gives us a formal specification in a language that we have. It's called Sokai. We can also write some correctness properties of the system. For example, we can base those on vulnerabilities that have been discovered. We could say that at no point ever should a processor core that is not operating in ring -2 do an instruction fetch to a region of memory which could possibly have been written previously by a core executing in a ring other than -2. That specifies that, an AMD sync close vulnerability cannot exist. Okay, so we can write specifications like that. What we can then do is analyze those, see if there are any problems. Not only can we generate sort of potential problems here, we can also generate unit tests to run this stuff on the real hardware and validate whether or not the problems we think are there are actually there. And so this involves turning this decoding network into a sort of an imperative program that is effectively a simulator for the very abstract sense for all the different parts of the system. So translations become procedure calls in this abstract programming language. The nice thing about all of this is that that becomes a program we can statically analyze. This looks like Rust, but it's not Rust. It's actually our own language. It's compiled using a compiler that is written in Rust, but it generates, at the back end, it generates input to various theorem provers, in particular SMT solvers and symbolic execution engines. So we can analyze this program, which is a simulator for what the hardware actually does. Okay. Transactions can be represented as types. So whereas in our old work, we couldn't actually say what the difference between a read or a write or an atomic operation or a trust zone secure mode versus non-secure mode transaction. Now we can represent all that using a type system for transactions. And these are the arguments to these procedure calls and the results from these procedure calls that come back. So we can now capture what the hardware does in a much more detailed kind of way. And so we can write specs like this. This is a simplified version of a component on the CPU for Enzian, which is a Cavium Thunder X1 CPU. It's called the address space controller, and it performs some rudimentary protection on regions of the physical address space. It either translates a request into a register read-write, or it checks permissions on a DRAM region and allows it or disallows it based on how you've configured it. So we can write little specifications like this. And then, before we actually go into the business of trying to fix the operating system, we can look and see if we can find any bugs in the hardware. And so this is the sort of where we are at this point. So for instance, here is a function that we've written in our little language that expresses the property that in the example, the previous hardware example, which is part of this module, in less than or equal to 2 different steps in time is represented here in a particular kind of way, a non-secure code cannot modify memory that is owned by secure mode, a ARM trust zone code. Okay, and so here is a set of assertions, and then here are 2 time steps, and then this is checking whether anything has actually been modified. Now these are unbound variables. This is going to be executed symbolically. So these things have potentially any value, and it's the job of the symbolic execution engine to come up with values that might fit these. If there are values, then we have an interesting situation on our hands. So at each time step, a request is issued, so either a read or a write, any address, any value, and the current secure or non-secure mode of the processor. And these functions could somehow advance time, or they could not advance time. Most of them don't, but the critical ones do. And if we give this to Rosette, which is a symbolic execution engine, and we say, can you see if this function is ever true? This checking function ever returns true. It says, oh, sure. And it comes up with this. CPU does a request, which is a non-secure write of a value 1 to this address. And then here's the action. And then the CPU then does a non-secure write to address 0, which is supposedly secure, it's in trust zone, of this value. This is a completely random value that it's made up. But it happens to be a value that works. And what happens here is that it stores this value to trust zone memory. So what you've done here is it's found a configuration of that protection unit that violates trust zone. And that means that trust zone is essentially broken on that chip. Right? We weren't quite sure whether this was true, but it turns out it is true. It is a bug on the chip. It was not known before. We've reported it subsequently to Marvell. The chip isn't made anymore, so it's unclear whether they really care about it. But it was interesting to us that we did this, okay? Now, this was done basically translating the manual. So you should be worried about whether this makes any sense in the real world. And so this is really the nature of the guarantees we're sort of providing at this point in the stage, right? There's the question of whether the hardware is actually safe or not, okay? If the hardware isn't safe, right, if there's a bug in the hardware, then the question is the documentation. Is that faithful or not? Because bear in mind, we're typing this in from the manual. So if the documentation is faithful and we've typed it incorrectly, then Sockeye is going to find a hardware exploit, as it did then. It actually pops out the sequence of register writes that you need in order to violate some security property. If the documentation is faithful, if it's not faithful, if there's a bug in the documentation and the hardware has a bug in it, we're not going to find anything. And that's the main limitation of this approach, is that if the documentation says everything's okay and the hardware isn't okay, there's nothing we can do, right? This is not a way of automatically, exhaustively testing hardware. But if the hardware is in fact safe, then the question is the documentation safe? If the documentation is safe, then we can check whether the configuration is safe. And if it is safe, then we've got a proof using symbolic execution that this configuration does achieve all the security properties. That's a useful thing to have. If the configuration isn't safe, we found a bug. If the documentation is wrong, but the hardware is fine, Sockeye finds an exploit and we try it out. We've got an immediate test case and we can figure out whether this is a documentation bug or not. We can either find out whether it's this case or it's this case down here. So this is kind of an interesting sort of job. And so, we had a bunch of SOCs and we had a bunch of students. And so we gave them to a bunch of undergraduates who wanted to play around with operating systems and formal methods and things. And we gave them a load of manuals, again, 8 different SOC manuals that we had with chips, and they could write code, try things out. They reproduced 2 hardware bugs that were already known, but purely just from the system. They produced 1 new hardware bug, the ThunderX bug that we didn't know about. They found 4 different documentation errors, which are then verified by actually testing the real thing in the real hardware. It's very easy to do that. And they also found 2 serious configuration issues that were not well documented. So these are things that where the documentation is kind of, a lawyer would say, there's nothing wrong here. But unless you really know what you're doing, you're liable to get it wrong. For example, one of the SOCs, the Ethernet card doesn't respect trust zones security. And so you can program the Ethernet card from the non-secure world in order to DMA stuff into the secure world. So you can jump through the Ethernet card, even though it's not a programmable Ethernet card. You can get it to DMA memory like into secure memory and compromise secure memory in that way. Now that is not a fatal bug. It just means that you have to put the whole of your Ethernet driver into the secure mode, which is something that many operating system designers would balk at. That seems to be an awful lot of, code in your trusted computing base at that point. And we found lots of ambiguities in the documentation. The nice thing about the specification is that because it allows these any values to be put in there, you can encode the ambiguity in the document, in the specification. You can say this value is one of the following ones we don't know, and then it'll investigate all those paths, and then you can see which of those paths actually correspond to reality. The long-term goal, of course, is not to actually find bugs. Finding bugs is kind of fun. It's great. It's a good project for lots of students. But ultimately, we want to do something constructive here. And so we really want, this is the end of the talk, I suppose, we want an operating system for real computers, a real operating system that does what an operating system definition says it should do, that actually does manage all of the hardware in the system, and yet about which we can make strong formal statements about trust, integrity, correctness, and so on real hardware. And that replaces the de facto operating system with something that actually has something of a design, and in particular has a specification of correct behavior. And it may well be that that's going to reuse a bunch of components, right? But it's going to actually say what it means for different parts of an enormously complicated system, even like this on a single processor, let alone a very heterogeneous SoC, bits to actually interact. What would it look like? We're in the process of doing that right now. It has to be built from a bunch of existing parts. Sometimes you just can't change the software for legal reasons, regulatory reasons, proprietary reasons. So there are components that you just cannot change. They're fixed, but somehow you have to design the OS around them and ascribe certain properties to them. Maybe you don't trust the firmware in the Qualcomm modem, in which case make sure that at no point can it compromise the rest of the system, and verify that. And you can do that, in principle, using the kind of framework that we've got. It's also got to be, to be realistic as an operating system, we can't engineer it all from scratch. We did that once, it was great. This has to be able to reuse existing parts, and it also has to support, a wide range of existing applications and a wide range of hardware platforms, which means it really needs to be parameterized by the kinds of specifications that we're writing. But if we can do that, then we end up with an operating system for real computers, a true operating system It's going to have to be a distributed system of components. It has to be a multi-kernel in the way that Barrelfish was, because it's running on a whole bunch of distributed cores. However, it is not like Barrelfish in that it sense it has multiple trust domains. Barrelfish assumed that there was only one, everything trusted everything else inside the OS, much like a classical OS. That's out the window now. One part of the OS cannot blindly trust another part of the OS anymore. We're just not living in that world. So it has multiple trust domains. Some of these parts may be verified, some may be not. And so the trick is to be able to use the verification proofs, figure out where they apply and how they can be made to apply and made to provide real guarantees to the system. And that involves essentially explicitly representing which bits of the system trust which other bits of the system at all times. And that's really what we're doing, right now. That's sort of the meetings that we're having now. There's bits on my whiteboard here that describe that kind of thing. And I've given you sort of, some ideas as to where we're going to go with this stuff, but a lot of it is very, very open. But I noticed that it is 29 minutes past and 30 seconds, so I will finish with a slide with, acknowledgements. This is my group right now, but also many, many, many people in the systems group at ETH have contributed to Barrelfish, to Enzian, to a lot of other projects, to Sockeye, and the current work we're doing. And so it would be remiss of me not to mention these. But with that, I'm done. Thank you very much. I hope I didn't overrun too much. I'm just under half past.
Perfect. Thank you very much, Timothy. Very, very nice talk. Very enlightening. I'm looking at my computer with different eyes as of tonight. Any questions? Yes, I've seen the first one. Charles, please go ahead.
Thanks for a really fascinating talk. So what I'm wondering is, if you are given a system and with some documentation that goes along with it, is there any way to determine if the documentation has completely ignored or hidden part of the system, which could then lead to a compromise later on? Deliberately doing it.
Yeah, like someone's done a supply chain attack or something. Yeah, I mean, obviously the documentation is exactly what it says. It's just documentation. So with the stuff we have right now, okay, there is a class of properties of the system and a class of, aspects of the system that if the documentation is silent on it, we do not detect that. We can't prove, we can't prove the sort of absence of a negative here. So we can't currently do that. To do that properly would involve literally exhaustively testing everything about the SoC as a state machine. Theoretically, that's not really feasible, right? It's completely unbounded. You've no idea how big the state space is inside one of these things. And so in practice, if somebody just gives you a box containing an SoC and a manual, you have no way of knowing what that SoC actually does. You can say whether the SoC does what the manual says it does. We can do that. What we can't say is whether it does something the manual is silent on. Now, there are a few things you could do to improve the state of affairs and what we're doing. So one of the things that would be interesting for us is that because we can take the spec, that's a very abstract description of what the SoC can do. You could imagine trying to figure out whether the RTL, the Verilog, or some low-level hardware description actually refines the spec that we have. And so one of the things that we can do is compile, we haven't done this yet, but it's certainly it's a thing on our list, is to compile our specification into Verilog and create a ludicrously simplified version of the SoC that you would never actually build for real, but it is a hardware description of something that implements our spec. Then you can use Verilog equivalence testing tools, which are quite good in the commercial sphere, to see whether that's equivalent to the Verilog you have of the real implementation. That, of course, doesn't solve your problem, in that you've no guarantee that the Verilog they gave you for the system is really what came off the end of the fab line. But that also gives you another way to slightly close the loop and to sort of figure out how close you are to the real hardware. So yeah, the short answer is no, but it could be worse.
Okay. Thanks. Any more questions? maybe I just have one in between. With all the shortcomings and deficiencies that you explained in systems nowadays, if we could get rid of those, would this have any impact on the performance of a newly designed operating system, for better or for worse?
Oh, if we could build better hardware.
Yeah.
Oh, sure. Operating systems people have a long history of being frustrated with hardware designs. And the reaction is typically passive aggressive. We just moan about it in the pub among ourselves and never actually go to the hardware people and complain about it. Part of the reason for that is that it is very hard for operating systems people to actually say precisely what is wrong with the hardware. And one of the, I mean, that frustration is one of the motivations for this work. But it does mean that there's a possibility now that you could, using this kind of specification approach, you can then go back to hardware people and say, your hardware did this. This, I think, is a problem. Could you have done it this other way? Another thing we could do as well is we could say, we can take our specifications of different pieces of hardware that do essentially the same job and look at how complex they are and run standard complexity metrics over the specifications, and then go to hardware and say, look, your MMU, we can specify it completely in 3,500 lines of our, thing, whereas the, brand X's MMU takes only 1,500 lines of specification and appears to do the same thing. What's up with that? And it would be nice to come up with, for system software people, to be able to come up with some guidelines for what. I had a conversation with Richard Gristenthwaite, about the chief architect of ARM, many years ago, and he sort of said, what is tasteful hardware? And this is a way for operating systems people to try to come up with a definition of tasteful hardware that then they can take to the hardware vendors. Say, look, this is a nice piece of hardware. I have to say the ThunderX chip that we have in Enzian, I think is quite, it has its bugs, but it is quite a tasteful piece of hardware. It's nicely designed. But I only discovered after that, by talking to the founder of the company, that, yeah, he started off as an operating systems person and went into hardware design out of frustration. So.
By the way, how long did it take you to build this Enzyme?
Long time.
Okay.
We're a university group. Building a 28-layer board at 10 gigahertz at EATX size was an adventure. I suppose from originally just conceiving it and looking at parts and things to actually having a working version was, I suppose, a little over 4 years.
Okay. Okay.
We did learn an awful lot on the way, though. It was a kind of fun thing. And now we have our own computer. It's great.
Nice. Very nice. Okay. Any more questions? Any more questions, Timothy?
Certainly, I imagine for people in Geneva, I'm standing between you and evening cocktails, so I can quite understand this.
Okay, I don't see any more questions. 3, 2, 1. Okay. Okay, so thanks a lot. Thank you very much for very enlightening talk. And
pleasure.
Yeah. And so that concludes the Compute Accelerator for today. And we're going to restart in 26 with new topics. Okay, thanks, and have a good night, everyone. Good evening, everyone, or good day. Bye-bye.
Bye.
Bye-bye.
Bye.